Welcome everyone to our monthly Science of Alt Protein seminar. It's so fantastic to see our global community join us for this very exciting presentation by members of the Cultivated Meat Modeling Consortium. We have a pretty packed lineup today, which I'm really delighted about. We have almost 10 speakers from the Cultivated Meat Modeling Consortium. So we'll pretty much dive straight in. I'm really jazzed to have the CMMC here in attendance with us today because I think we as a community have a lot to learn from their many experiments and models. Basically, their mission is to utilize computational modeling to accelerate the optimization of processes and products for cultivated meat. I think it's been a known white space for a long time to apply computational sciences to the alternative protein field so that we can be much more efficient at understanding our technological bottlenecks and then accordingly overcoming them. So I think there will be lots of insights that come out of today's presentation. And I will go ahead and turn it over to Dr. Simon Kahan to get us started.
Okay, thanks.
Hi, I'm Greg Potter, a bioprocess scientist at Lipiform Scientific.
And I'm Simon Kahn, a computer scientist at BioCelliant.
And we're here on behalf of the CMMC, along with 8 others, to tell you about a couple cool, innovative modeling projects we have on the go. But before we begin, it's helpful to understand what exactly are the reasons we need innovation. To help answer this question, it's useful if we refer to Dave Humbard's seminal techno-economic analysis on cultivated meat. And here we see just how much biomass we are going to need with present-day bioprocessing infrastructure to support the demand for conventional meat. Of course, many of us have done these kinds of back-of-the-napkin calculations, but it is helpful to look at these sobering numbers. Now, 150 grams per liter of biomass is the maximal cell density that Humbard predicted we could produce in 20 cubic meter stir tank reactors. But in reality, few companies today are hitting those kind of biomass targets, the claims of future meat aside. In fact, it's hard enough to get those numbers even with CHO cells, which have undergone decades of process optimization work. So therefore, innovation is needed if we are going to hit the biomass targets, which will allow us to actually support the demand for conventional meat using cell-based approaches. And here we believe computational modeling can help. However, it's not as if applying computational modeling to bioprocessing is new. In fact, pharma has been doing this for decades using computational fluid dynamics, mass transfer modeling, and so on. So this begs the question, why does innovation in cultivated meat require new modeling methodologies? And what's wrong with just using the existing computational tools at our disposal? So the answer to this lies in part in the fact that the cells used in cultivated meat bioprocesses are unique in that they are more sensitive than, say, microbial cells, and they cannot be disturbed too much. In this vein, Dave Humbard has done a great job defining thresholds for mammalian cells generally by making inferences from the literature with an emphasis on CHO cell reports and constrained yeast fermentations. However, these numbers are inferences made for CHO cells, and in reality, there are many different cell types under consideration for cultivated meat. Now, at present, computational modeling tools primarily rely on simulating the environment within the bioreactor and don't take into account cell biology. So given the diversity of cell types, which will be required for cultivated meat, we clearly need new modeling methodologies that take into account the cell experience.
So our working hypothesis is that incorporating explicitly the cell experience, like the fluid forces or oxygen deprivation that the cells endure in a bioreactor, and also incorporating the cell responses to their experience, like that their proliferation slows down or that the cells die. If we incorporate these into models of bioreactor systems, we'll make the models more useful especially for delicate cultivated meat cells. I should say that by useful, I mean generally reducing the number of large physical experiments needed to develop efficient production processes. That's kind of our commercial goal. There are two projects in the CMMC underway that are testing our hypothesis. They both relate to combining cell biology with models of fluid environment, but in very different ways. They're called SkillUp and Scale Down modeling. In the case of SkillUp modeling, we virtualize bioreactor experiments. We replace the cell, media, and bioreactor by computer models that we simulate to get a prediction of how fast the cells will grow, so what the yield will be. We do have to run a bunch of laboratory experiments first on the particular cell and media of interest to get the insights and data needed to inform our models of the cells. But once that's done, the goal is then to use the computer only and get predictions of yield as a function of bioreactor geometries, impeller speed, and so on across bioreactors that are diverse in their scale and design. Yarrow, Fernando, Rick, and Boris will present progress on the scale-up modeling. Scale-down modeling is also in service of reducing the number of large physical experiments, but it's completely different. Small physical experiments or assays are used to choose the most promising candidates from a number of cell lines or media formulations. Scale down modeling is about making sure in these small experiments that the cell experience, the stress, the oxygen, and so on, are in fact representative of what the cells would experience at larger scale in a bioreactor or just in a larger vessel. So the modeling isn't of biology, actual cells are used, but of how the small scale environment depends upon things like vessel shape and agitation. Simon Hubbard, Daniel, Radu, and Luke will present their work on scale down modeling. A couple of comments about the projects before we start. They're both intended to generate methods that are generally applicable, and that means across the cultivated meat space, whether it's chicken or fish or whatever, and for diverse growth processes. So it means we don't need the details of media formulation or of the cell line, though obviously we need some samples. And we also bypass what is a very common hurdle in modeling biology, the detailed intracellular models that can consume an entire career to develop and validate. We want to create tools that are generally useful and available in years, not decades. I'll pass the baton now to Yarrow, whose team will talk about scale-up modeling. Thanks.
Thanks, Simon. So as Simon mentioned, we will be talking about the scale-up modeling, and scale-up is very relevant in cultivated meat because we need lots and lots of meat to feed the world population. The problem is that running experiments with these large bioreactors, let alone even build them, is going to be very expensive, and to explore all possibilities of the bioprocesses in these bioreactors will be impossible by doing it by trial and error. So we are in need of a better method, and we think that computational modeling can help here. So this is the intended final product, or one of the intended final products that we can put in the hands of cultivated meat companies. It is a dashboard where you can have on the left column settings for the model that you want to run. You can upload a vessel geometry or pick one, probably select its size or tweak it a bit, set some system variables, some variables about your cells, and then run a simulation. And that will look a bit like this. So in the middle panel, you have a 3D visualization of your bioreactor of choice. And you can view the microcarriers if you have them in there, or just cells floating around. And you'll have live updating analysis of what's happening in there. So you see the number of live cells, dead cells, etc. Something that tells you about the media concentrations in there. And you can view the particle densities in the bioreactor, because they tend to become much denser at certain locations. And this can help cultivated meat companies in assessing whether a certain bioreactor design can be useful or not, or we can do some sort of optimization of bioreactor and bioprocess. Now, how to build such a model? That's a challenge of its own. So we start off with a fluid model, which is a proven method in industry, even for large-scale production. And the capabilities of such a model in computational fluid dynamics are pretty diverse. So you can simulate fluid velocities and pressure. You can simulate the mixing of different fluids and gases, and you can get an impression of what the shear and turbulence at certain locations in the bioreactor will be. You can also model the movement of particles in there, and therefore how they will concentrate at certain locations, if that's the case. And you have the ability to model the full bioreactor depending on the resolution that you choose. However, we miss the cell biology, so we want to incorporate that and couple that to the fluid model. Now, we pass on the velocity and pressure and concentrations at any location to our cell model, and the cell model in turn can return local concentration changes and viscosity changes to the fluid model. However, we need to know how these cells react, and therefore we need to implement cell behavior rules. So each cell is simulated on its own, and it has certain rules, and these tell you the effect of local forces or concentrations, for example, glucose, oxygen, or waste products, and tell you the effect of these on the cell cycle and adhesion and possible metabolism. Now, how to get these rules? Of course, you need to run experiments to find out how these cells behave, but you can do them on the small scale for various circumstances. So run different types of flow over there with different concentrations and see how the cells react. And these cell behavior rules you then implement in the model. Now, we need to get some sort of boundaries for what types of environments we need to do the experiments for, and that you can get from your fluid model. Of course, we need to validate this, the fact that our model is actually representative of the experimental system. So we do some validation with the modeling setup in the experimental setup. So you have some small scale models and then boost it up to the large scale bioreactors. Now, next, Fernando, Rick, and Boris will present the pieces of this puzzle. So we have Fernando talking about fluid model, Rick about the cell characterization experiments, and Boris about the cell model.
Thank you, Jaro. So I'm Fernando. I'll be talking about the CFD part of the project. For those of you that have used computational fluid dynamics, you know how flexible it is. Jaro already explained a little bit. I'll be showcasing some of those scenarios that we have modeled ourselves to kind of understand the cell environment. So a simple model, so we are all on the same page. We have this cell and it needs something to attach to grow, which is where the microcarrier comes in. We have a flow coming in and then it goes out the other way. We consider the microcarrier to stay static in this position, and we run it through the computational fluid dynamics. What can we do? We can get fluid velocities and pressures, and also we can calculate shear stress that the cells will experience in this microcarrier. And so you can see by the images here, it's very detailed, and every single point in this graph can be extrapolated and used for other or passed on to the biological simulations. However, we of course want to see what's going on at the full bioreactor scale, and that's where the stirred tank or sprinter flask, which is the most common, comes into play. We have a proof of concept. I think there's a white paper out that we worked on, and again, we can see all the velocity profiles. The shear stress can be showcased very easily, and also we have Kolmogorov eddy lengths, which are significant because we know that they might damage cells depending on their sizes. And all of this information can be gathered from the CFD and passed on for the biological aspect of the simulations. We can also model particles within the CFD. That way we can have their trajectories. If there's some turbulent flow, we can see here we have a scanned impeller. We actually got the scan from something similar from what you see on the slide. And this is very important because we can see when the impeller impacts a particle, how this will behave. We can calculate the stress that this particle is under at that precise moment, and we can definitely determine if this will affect negatively how our cells are growing within the whole bioreactor. And although this is the most typical one, we of course want to go into other bioreactor designs because it is not the only one. We also have some more novel designs that are still not commercial. They might be coming out soon. We have no idea. In this case, we have one that has some plates where the cells will attach to in the middle, and it's continuous flow, so the media is constantly being replaced, and it allows cells to grow in a better way and will provide more yield. And with CFD, we can actually evaluate this and inform the biological model. We also have rocking bioreactors, which are very commonly used. These might not be used as much for a full-scale industrial, but there are very big bags for these, almost 20 liters. I believe there's also like a 50 liters or something around that area that we can see. And as you can see on the simulation on the right, you can characterize the shear stress, and just like before, you can see how it changes through time, which is very important for these simulations. But of course, as was mentioned before, we need to validate all of this simulations with experimental data. And this is where the Ibidi microfluidic chamber comes in. We are currently working with Rick to have some experiments done, and he will talk more about that. And we, on my side, we're doing the simulations to show all the different velocity profiles and shear stresses that could come from this system itself.
All right, my name is Richard Thud. I'll be giving you guys some information on our thoughts about actually informing some of the systems that were just talked about. Next slide. So, as I mentioned, we're going to be encountering, as a field of cell ag, every single company, every single attempt at scaling up the production of lab-grown meat. Everyone's going to have their own bioreactor. Everyone's going to have their own design and their own ideas. But as long as there's media being flown and passed over cells, the implications of that flow is going to need to be appreciated when it comes time for us to actually predict how the models are, or how your production system is going to perform, right? So in the event you have low shear, just across the board, and yeah, maybe the cells will be just fine and they'll grow and they'll divide and we'll have a system that's going to take us to the next level. But that might not be the case. You have a system where high shear is introduced. I mean, that could have a detrimental effect on your cell type. And remember, this is any cell type. This could be adipocytes from cow, goat, pig, fish. Could be muscle cells. It could be tendon. Name your cell type. Each cell is going to be responding differently. Also, think about your media as well. Every single media formulation is going to have a different impact on your cells. So the use of different experimental systems and with like clever experimental design, you can elucidate as much information as possible to really, really inform these systems. So the example that we're presenting today is this microfluidics device within which we culture cells that recapitulates both a traditional culture environment that you might encounter in like a basic research lab, but we can also impart the types of forces and the environmental conditions that they might be experiencing in large scale culture systems. In this case, we're we're passing a flow over the cells that are cultured in that two-dimensional channel. And we're going to be exploring how the cells are responding to that flow. Next slide. So yeah, like I said, every single reactor geometry, every media formulation and agitation regime that you're using to support your cells will have impacts on your ultimate system. Thus, based on your system, based on the computational fluidic models that Fernando was talking about that can be generated about your system, let's take the shear stresses that he's predicting that you might encounter and reestablish those conditions on a simple, cheap, easy culture environment, so that we can be really, really tactful with data generation, and we can generate as much data as we possibly can. Next slide. So inside of that IBD device, that microfluidics chamber, you can do classic biological destructive testing where you can count nuclei over time. You can perform biological live dead analysis and look visually to see at how your cells are responding to the shear stresses that we're passing over it. You can do immunohistochemistry to look at subcellular markers like PAC7 if you're culturing satellite cells. That way you can attempt to quantify how cells will respond in terms of the upregulation of these different markers that every company might be interested in. And also with this device, we can do non-destructive testing where the cells actually, they maintain their viability. So we can see over time in respect to the shear stresses that the cells might encounter, changes in the cell morphology, which is often an indicator of their differentiation. We can look at their growth behavior, their expansion capacity and cell size, etc. Next slide. And lastly, once this data is generated, it can really inform those predictive models so we can understand exactly how your respective cell type will respond to your respective growth environment. Some examples of what this data might look like. Everyone knows about doubling time and how maximization of that exponential growth is going to be key. I mean, we've already seen that just different cows, even the same age, they have different doubling times. This is something that we can explore under shear stress as well. We can look at Ki67 expression. Ki67, it's a marker for a cell's capacity to proliferate. So if a cell is no longer has the capacity to proliferate, then we know it's not going to be contributing to that logarithmic exponential growth. And lastly, a key component is going to be the cell adhesion under the shear stress. I mean, these cells, they're cultured on microcarriers in suspension. Their ability to attach and remain attached when exposed to shear stress or when encountering turbulence or these Kolmogorov eddies, what's the likelihood that they will attach? This information can be fed back into our models, and then we can hopefully elucidate a little bit more information on how our cells will respond at the large scale. All right.
Thank you, Rick. Hello, everyone. I am Boris Aguilar, and I will be focusing on the cell model. Next. In order to make predictions about biomass production in bioreactors, we need to develop a model of how the cells behave under fluid flow. And our strategy is to use controlled systems like the EBD chamber to generate experimental observations and use those for model selection and parameter calibration. We will be focusing on cell adhesion and cell proliferation. And then obviously we want to use these models to then use it in a bioreactor. Next. We included cell adhesion in the model because the number of cells in the EBD system or living cells depends not only on cell proliferation, but also on cell detachment. And there has been studies that shown that cell proliferation and cell adhesion are coupled. That the cell shape changes during the cell cycle, and those changes affect the magnitude of the cell adhesion between the cells and the EBD surface. Our model includes the number of bonds between the cells and the supporting surface, and how these bonds, how the number of bonds change due to a fluid. When the force due to these bonds are smaller than the force from the fluid, then there will be an detachment event. That's pretty much how the model works. Next, please. For cell proliferation, currently we are implementing, or we already implemented, a cell cycle model, and this was developed by John Tyson in Virginia Tech. This model includes important molecules like cycle E, cycle B, and cycle A, and also the biomass of a cell. And in these figures, you see the periodic behavior of these molecules and biomass during the cell cycle. And the idea here is that we will be using the concentration of one of these molecules and combine it with the number of bonds from the cell adhesion model. And so that's how are we going to combine proliferation and cell adhesion. Next slide, please. We have some results already. In the left panel, you see the cell growth from experiments that Rick generated in blue. And in orange, cell growth using the cell cycle model. These were obtained assuming there is no fluid. And the idea is that this type of data will be used to calibrate the cell cycle model parameters. In the right panel, you see simulations from the cell adhesion model that shows how the number of cells attached to the EBD surface changes in time. And this will be used to, it will be compared with the EBD experiments so that we can calibrate our model in this way. Next, please. These are all in progress, but the idea is to use the model and the calibrated parameters in other setups. For example, when the cells are growing on top of the microcarriers and in a bioreactor, or when the cells are growing in surfaces in this in different types of geometries of the bioreactor, that like the cellular revolution. That's all for me. I think we can go now to the next component of the presentation, which is the scale down. Thank you.
Thanks everyone from all of the SkillUp team. I'm going to introduce the scale down project now, which is focused on going in the other direction in some regards. So here we're thinking about replicating the behavior and performance of large production scale bioprocessing equipment at smaller scales. And so just to give you an idea of some of that scale difference, you could be talking about a large bioreactor that's tens of thousands of liters, and we want to replicate the performance of that in something that's got maybe a few liters, maybe microliters, milliliters, depending on how far you want to go. So quite a big scale change. And the reason we want to do that is so that we can optimize the large scale production process easily and quickly and cheaply at the smaller scale. It's much quicker, much faster, much cheaper, much more efficient to make changes at the small scale to understand performance than it is to do that at the larger scale. So there's a lot of different ways that you can start to understand how to do this scale down process. You can look at things like the geometry of the reactors. You can start to take some direct measurements at the large scale, look at some of the aspects of cell physiology, cell reaction dynamics that some of the previous slides have been talking about, to use computational fluid dynamics as well. One thing that we're looking at the moment is something called regime analysis, and that tries to understand where your operating windows are in the large scale and the small scale. So the graph on the right here gives you an idea in terms of how much you're aerating your media in your bioreactor, the axis on the bottom, and how much you're agitating it, stirring it using impellers on the top. And you can see that there's an operating window that you want to be in where you're aerating and agitating enough for the cells to be able to grow successfully, If you're too low, you won't have enough mixing or mass transfer across the interface. And if you do too much agitation or too much aeration, then you can damage the cells through shear stress and some of the other methods that you've already heard about. So with this understanding of regime analysis, there's lots of different regime aspects that you can have a think about and have a look at. And there's a few listed here for you to have a look at. So you can look at how geometrically similar things are, how fast your impeller's moving, the rates at your dissipating energies, how quickly your gas bubbles are moving through your media and things like that. So in this piece of work, we're focusing very much on the interfacial mass transfer and primarily looking at oxygen transfer across the interface. We're paying a little bit of attention to induced shear stress for the reasons that you'll have heard, and the mixing time within the bioreactor. So what we're thinking about here is the rate at which oxygen can be transferred from the gas into the interface and from the interface into the liquid media so that it can be absorbed and used by the cells as they're growing. And this process is characterized by a particular metric called KLA. The KL part describes a physics mass transfer rate from the interface, and A describes the area of the interface. And we're doing this in 3 different ways. We're doing some mathematical modeling, some lab measurements, and some numerical modeling or CFD, and bringing those 3 together to try and give us a good understanding of what's going on from a mass transfer perspective, but also giving us a range of tools and understanding so that we can come up with predictions and behavior estimates very quickly and effectively. So I'll hand over now to Dan, who'll take you through the mathematical modeling part.
Thanks for the introduction, Simon. And I'm going to share some of our results from trying to develop, using existing data, trying to develop a simple mathematical model where you can come up with a single formula where you can try to predict these KLA values, which are so important for different agitation conditions. So the primary data that we're working off of as we're collecting our own and doing our own simulations, you'll hear from both Luke and Radu on those aspects later on in the talk. But this problem of agitation at small scales is certainly something that's been studied in quite a bit of depth before. So there's a wide range of data sets. The one we focused on is this experimental set from Herman et al. In 2002. And they focused on a 96 well plate that was agitated on an orbital shaker. So these things are moving around on a circular orbit with some frequency and some diameter. So again, focus on the right axis here. So this is that KLA parameter that gives you an indication of how efficiently oxygen can transfer and then mix into the bulk. And on the horizontal axis, you see the shaking frequency. So generally for each of these curves, which correspond to different shaking diameters, you see as you shake it, you agitate it more vigorously, whether it's a larger diameter or you increase the frequency, you get more mass transfer. And this is in general why we agitate these types of systems. So we don't have to rely on pure diffusive processes alone, which are known to be quite slow. So in studying this preliminary data and thinking about how we might develop a simple model to capture some of this behavior, there's a few experimental observations from this paper that stood out to us. One in particular, they noted that for circular wells, round wells with a circular cross section, which are the most common used in application, it mentioned that this KL factor, the KL part of the KLA, this mass transfer coefficient, remained about constant, were independent of shaking intensity, so meaning both frequency and diameter. So what's left then, of course, the A part, right, must be changing if KLA is in fact changing. And the other thing they noted here, which was an important observation in developing our kind of physically informed model, is that the oxygen transfer velocity is independent of the fill volume. So that's another parameter I haven't shown here, of course, is that it's going to depend on how much you put into the well. But what they notice is that the initial, or the rate of transfer in something like a moles per unit time is independent of the fill volume. So really what that led us to is a hypothesis in these systems, again, based on this existing data, is that the KLA and the oxygen transfer is predominantly due to increase in the area part, or because you're agitating this, you have a larger surface area, so more molecules of oxygen can interact and get to the bulk. So in studying this, of course, we're working with collaborators using orbital shakers, and this is an example from YouTube of an orbital shaker. But what I wanted to emphasize here is that you can see as it orbits, it essentially forms, at least at these conditions, it essentially forms a flat plane that rotates in time. Right? So in that plane is, because it's a larger cross section, is going to have a larger area. And you can do this, you've probably done this and you haven't realized it, by swirling your glass of wine, or maybe you have a cup of coffee with you. And if you do it relatively slowly, again, you see kind of a planar surface form, which has a greater surface area than just a circular cross section. So it's a very convenient mechanism for increasing the surface area, regardless of the fluid motion underneath. And so if we try to develop a mathematical model based on these observations, we go back to our fluids 1 textbooks, and we know that if we accelerate a fluid, the free surface or the air-water interface is going to become aligned with the normal to the total acceleration. So now including both gravity and some kind of acceleration vector, which I'll call R double dot here. So as you slide this along, and you can think about, you know, stepping on the gas pedal in your car, the fluid's going to want to go away from opposite of the acceleration direction, right? And so in steady state, you'll get something that's a flat surface like this. Right, and you can characterize that angle of the cross section by the ratio of this acceleration, induced acceleration, to gravity. Right, and of course, in this relatively simple agitation condition, we have a uniform acceleration that's being applied, which is just the centripetal centrifugal force. And so you can calculate that as a velocity squared over a radius. So we can write that down in terms of both the frequency of agitation and the diameter of the orbit into one single number here. And so ultimately, we can try to make a prediction of what this angle would be depending on this fluid-induced fluid acceleration. Right? And so if we go back to our data, so this is the digitized data from the Herman paper, and we try to replot it now instead of frequency, but in terms of this acceleration, you can see that this relatively large scatter, which signified that the numbers depend both sensitively on frequency and amplitude, is significantly reduced, probably within of the experimental error as far as we can tell. So the advantage here of what we've already discovered without doing too much work is that the KLA enhancement can be characterized by a single parameter, which includes both the agitation diameter and frequency, at least under these specific conditions. Right? So it's already reduced our parameter space and the complexity of a rather large problem. We can go a step further. Again, now we've predicted this angle, and so we can think about these cylindrical wells, and we can think about the cross-sectional area. So our hypothesis is that the area is increased, and so if we know the angle, we're going to get a bit of a boost relative to the circular area as we had suspected. So if we combine with our, use our theta that we've calculated from the previous result, we can ultimately get a prediction for what is the new area in terms of the agitation conditions or this effective instantaneous acceleration. Turns out that this messy looking trigonometric combination simplifies nicely, so you can get a cleaner looking expression like this. And ultimately, the lowercase a that you see is a specific area, so it's area per unit volume. So we'll divide by the overall volume. And so when all is said and done, we can get an analytical expression for this A parameter, which seems to be what's dominating the change in KLA, as a function of our fluid depth, as well as the agitation parameters in bulk. Okay. And so now if we compare that prediction with the experimental data, you can see it does a reasonably good job at explaining the trend, maybe slightly worse so at large agitation conditions. But in the end, when all is said and done, to be able to make this prediction here, which gets us within 20–30% of the correct answer for all cases here, all we need to know is a single measurement. And so that would be a measurement, for instance, at no agitation. And then we can predict how that area increases and subsequently how KLA increases. So these early results are quite promising in the sense that, one, it's allowed us to isolate what are the key parameters in the problem, which is important for understanding the physics, but also when we go to experiment and computation, and be able to reduce our parameter space can save an enormous amount of time and costs. We've also developed a simple expression that could be used as a first estimate for KLA given agitation conditions. Some of the ongoing work is comparing with the full CFD that Radu will discuss, as well as the experiments to validate some of the assumptions of this relatively simple model. And the other thing that I'm actively working on is including the effects of surface tension, which for small scales, and as we scale down, we'll be working at small scales, becomes much more important. So these are pictures, actual images from this Herman paper of this agitation, and you can see at these large agitation rates, the surface is tilted, but you see some curvature due to surface tension. And so early work that we've done in including surface tension in this type of model shows that some of this missing gap in our simple model is accounted for by adding surface tension. So with that, I'll turn it over to Luke, who will present some of our new experiments, and then that will be followed by Radu, who's going to present some of our full CFD work.
So thank you so much, Dan, for that introduction. I want to talk a little bit more about the types of experimental equipment we're using to get the data that's going to help support some of these computational and modeling initiatives. As Simon and Dan both talked about previously, the objective of the work that we're doing is trying to take all of these different parameters and all of these different, components and things that we need to consider in order to optimize, cell culture for this process. Media type, nutrients, oxygen content, mixing rates, mixing periods, which would be extremely expensive to do in a large scale format, and scale that down into a 96 well plate so we can scale that back up later with the things that we find might work best. We use a deep well 96 well plate for most of the studies that we're doing right now, because that gives us a high throughput means to test many factors simultaneously. And it's in a format that's slightly larger than a conventional 96 well plate. So we still can, grow a lot of cells if we would need to, and do something that would simulate something at a larger scale. And also, as Dan said previously, we're looking at investigating how, oxygen diffusion is going to work experimentally, and essentially figuring out, what types of mixing rates and what types of speeds can we do to increase oxygen diffusion without adding too much shear onto the cells. So we use that deep well 96 well plate on a stirring platform to be able to agitate media that we're interested in at different speeds, which, on its face is not a super technical thing. It's something that we can do relatively easily. But then using high speed camera imaging and being able to look at all the stuff that we have available, from that recording, we can really get a good picture of what that interface looks like, and take that information to help support the work that Dan and Radu are doing to be able to evaluate these different conditions computationally and figure out how we can optimize oxygen concentrations in the media. But in addition to that, we're also able to run tests directly on the oxygen concentrations in the media using a system that we have in the lab to evaluate oxygen conditions in each of the wells. The system that we use has oxygen sensitive fluorescent foil probes that are at the very bottom of each of the 96 wells in the deep well plate. And putting that into a chamber where we can regulate gas conditions, we're able to evaluate all that information and put out media oxygenation data for all the conditions in the 96 well plate, and be able to, basically just evaluate that en masse. So it gives us a really good method to be able to evaluate a bunch of things at once and support the computational modeling. So that's what we're doing on the experimental side for this. And from here, I'll turn it over to Radu.
Great. Thanks so much, Luke. Hi, everyone. I'm Radu. My name means the cheerful one, and it's a function of the amount of coffees I have in a given day. I'm going to be walking you through the computational platform side of our work. And in particular, I will be kind of keen to tell you about how we started this off. So basically, we're using an open source package called Basilisk as a starting framework. And we'll do this for a specific reason. So this is our little Basilisk. It's a package and kind of a family of software that's very popular in the fundamental fluid dynamics community for a variety of reasons. First of all, it's got adaptive mesh refinement in both space and time, and second order accuracy, which are both very good things, like quite rare to find for research type packages in general. It's got good parallelization capabilities. So we'll run these types of calculations that I'll show you in a second on reasonably large machines and deploy them in such a way that we can exploit the architectures underlying those types of clusters. And in the right-hand side, I've sketched here some of the key points of the package in that it uses a type of refinement strategy that can focus around regions of interest, such as, say, interfaces in a fluid. And because of this refinement strategy that is based on so-called quadtrees or octrees, it then gets assembled into this type of tree, which makes it very nice to parallelize and distribute across these larger scale machines. Now, the other benefit is that it's really good at handling multi-physics type problems. And in particular, if we want to start from a typical fluid dynamics scenario, but are interested in adding more features onto it, it supports these types of developments and gives us full handles over the computational architecture. And the languages that it tends to rely on are reasonably well known. So it's based primarily on C, but there's also a bit of Python, shell scripting, and some visualization aspects involved that we're going to make use of. So all in all, the package Basilisk and its predecessor Jeris have been around for about 10 years and have generated hundreds of papers for the CFD community, and they're very well validated, which is why we started them as a good starting point for this body of work. Now, what lies under the hood? I'm also an applied mathematician like Dan, so I'm not going to spare you the equations, I'm afraid, but just going through them relatively high level mode. We'll start from the typical fluid equations that you may have seen. These just represent the conservation of momentum and mass. And some of you will notice typical convective terms, pressure terms, diffusion terms, and this is the term that represents surface tension. And this represents the conservation of mass in this particular case. And what ties everything together is what's called a color function. So in these types of codes, what we solve for is the movement of the fluid, both the liquid environment, but also the gas, because remember, we are interested in the oxygen transfer properties, and we are interested in modeling what happens not only in the liquid, but in the gas as well. So underlying these objects that denote, say, density and viscosity, what lies beneath them is really a way to also navigate the space between the gas and the liquid and have a unified description of everything. And then, of course, one can adapt the interface once you know the color function and you know the velocity field therein, then through some clever algorithms, you can move this interface around and propagate your solution forward. Now, this is the more traditional fluid dynamics side of things. And if there are some of you in the crowd who are experts in CFD, you'll recognize that this is what's called the direct numerical simulation framework. So rather than thinking of approximations or assumptions in the flow, we just take the natural form of the equations and we attack them directly, which gives us the benefit that we don't have to add any fitting parameters or any extra approximations, but we do have to, of course, account for computational and discretization errors, which is where the adaptive refinement, for example, comes into play. Now, as we move into our particular problem, there was a note that we also need to take into account a bit of extra physics, and in particular, the transfer of the oxygen from the gas into the liquid. And this is done through a variation of Henry's law and implementation thereof. And each of the media comes with their own diffusion coefficients. And what you tend to do is, on top of all the fluids problem, you solve in a coupled way an advection diffusion set of equations. Again, simultaneously in both the gas and the liquid. And there are some technical details that tell you how exactly to navigate that interfacial region, which is so important to us. But yeah, what I want to kind of convey with this slide is really that we have access to everything underneath the platform itself, and we can modify them and adapt them to our problem. And in particular, for the scale down application that we're interested in, we really benefit from having this very detailed view that we can then build on for our particular geometry and results. Now, we also need to communicate with the experiment. So the value of such a platform, at least in my view, is one in which it can both inform experimental and modeling progress, but also draw information from it in an accurate way. So what's on the menu in terms of how they cross communicate with one another? Well, we're gonna need a few parameters, and the geometry and motion aspect has already been described. So we're looking at these types of well plates with a certain sizing, and we also impose a motion, the orbital shaking that was previously described. So the shaking radius and the RPM comes into play. We also look into physical parameters. And what tends to happen here is that we get a whole host of density, viscosity, surface tension coefficients, fill levels. But luckily, with some of these, they're either constants, or we have established through the mathematical modeling that we don't really need to take into account certain complexities that we were previously more concerned with. And finally, the benefit of having such a platform, as has been described for the SkillUp project as well, is really that you can create a digital version of one's experiment, but also increase the measurement capabilities and draw a lot more from it, where it would be difficult to image or to measure a quantity experimentally. So in terms of what comes out at the other end, I'll share a sample of what we're currently working on. The type of images that we get from our simulations look something like this, where I've evidenced the underlying grid, the contour around the interface, and also a bit of our geometry. And throughout this, we then are able to extract information around the liquid gas interface location, and we can do this with any desired resolution and then inform the type of KLA metrics in question. And we can customize measurement stations. And in particular, we have placed several tens and hundreds in some cases of locations where we monitor information in the flow. And this can mean velocity components, which then allow us to compute shear stress. We get pressure information, oxygen concentration levels, and this really inform at a very detailed level all of the higher level quantities we want to obtain as well. So I've given a few examples on the right in terms of pressure fields or typical contours of quantities of interest. But really, what I mean to say is that once you have access to this detailed data, it becomes very easy to then look into quantities around the global system itself, such as mixing and the KLA generation itself. And finally, because we have access to everything under the hood, it also means naturally that we can build on top of this and generate even more knowledge in questions. So I guess one of the key points I want to end with is the fact that we have designed this platform from the bottom up means that we don't have to include any approximated parameters. Many simulation platforms, for example, adopt KLA as an input parameter, but we actually resolve everything on the fly and output it and understand what are the fundamentals beneath its variation, and then are able to gear it towards our particular problem of interest, which is the scale down strategy at hand. So thank you very much for listening, and I'll stop here.
Well, thank you. Thanks, you guys. So as you can see, we've got a lot going on. We just, given the time constraints, you can only scratch the surface here. If you'd like to learn more and get involved, encourage you to check out the website, thecmmc.org. I'll type it in here. And if you're interested in joining, the consortium's open to everyone. There is a substantial membership agreement that that outlines the terms that may be a little bit overwhelming. If you have questions about that, you can write us, or if you have any other questions, yeah, you can write us at info@thecmmc.org with your questions there. But thank you very much for hosting and for attending.
Absolutely. Thank you so much, everyone. Holy wow. There's so much collective brain power here. It's remarkable. I'm so glad all of you are working to help us understand what the cultivated meat industry might look like as it matures and scales. Just throughout, I think it was really, really clear how powerful the work you guys are doing is in helping us avoid the very slow, expensive, iterative experimentation at scale, and how it can equip us with the predictive power to know how cultivated meat will behave at scale, and that giving us the ability to really 10x progress in this space. I know that you guys have done a pretty stellar job of answering the questions that came in through the Q&A section. To our audience members, if you guys have any additional questions, do feel free to add those in to the Q&A bar. But I wanted to start, I guess, in these next 13 minutes of discussion, I wanted to ask a question around, I think you guys made a nod to this at several points throughout your presentation, but it seems like a persisting barrier to being able to apply this type of a computational layer onto many of our questions is the lack of large publicly available data sets in the cultivated meat space. So I'm just curious if you guys have any, if you can speak to the size of that bottleneck right now and any efforts underway to kind of clear those hurdles.
So the kinds of data that we need to model often is not the kind of data that we can find in the literature. We have to have folks in the lab generate that. So you may have noticed there of all 10 people here, there were 2 experimentalists. We need a lot more. The CMMC could really use a lot of help from folks that like to run experiments in the lab and measure things and design experiments for measuring things with precision. I think that has been the bottleneck in developing models. It takes some time to understand the kind of data that we need. It's not the sort of data that biologists just tend to generate on their own, because we're interested often in the things that go wrong. Cells taken to extreme conditions versus trying to get them just to grow. We kind of like to kill them and, to see what their limits are. Yeah.
Thanks, Simon. I also, I recognize that what you guys are doing is really kind of extraordinary here. I don't know of a group of kind of computational biologists and computational science rallying around any other emerging fields. So I think this is a really cool project that you're undertaking. I'm curious if you can speak to any of maybe the biggest bottlenecks and challenges besides the lack of kind of experimental data, and whether there's anything that our community members on the academic or industry side can kind of do to help overcome those bottlenecks. That's an open question to anyone who might want to weigh in here.
I think related to the data question you asked, but a bit different is we always ask to experimentalists but also to companies, what is the process that matters? What matters, right? What do we need to incorporate in our model? Is it the adhesion? Is it the proliferation of cells in bioreactors? What are the problems in the lab? What are the problems that the companies are dealing with? And it's often really hard to get a unified answer that people agree on. This is the problem that we're dealing with. So that has been a struggle, I think, since the beginning of the CMMC.
Super interesting. Yeah. Any other, Simon? I saw you come off mute.
I don't know that I have anything to add, really. I mean, we would love to have more commercial members, companies that join that have problems that we can dig into. We can do that with under confidentiality agreements. We have that set up in our membership. So we'd love to, if there are companies that have problems that might be amenable to modeling, we'd love to dig in and help with those.
Awesome. Yeah, just a follow-up question. This might be too hard of a question to answer, Yaro, but why do you think the problem statement is so difficult to articulate? Why is it hard to understand precisely what it is we're having trouble answering?
I think actually because much is unknown about these biological cells. We at a certain point hooked onto the question of, okay, do the small tiny eddies in turbulence kill the cells or let them adhere from a microcarrier? And we got some people that said, yes, that's definitely the case. And others said, no, that's not happening.
Interesting. Yeah, that's super fascinating. Radu?
Yeah, I just wanted to add to Yaro's answer that another interesting feature for these types of problems is that what we call their multi-scale nature. At the same time, you are worried perhaps about devices which are meters in typical length scale, but at the same time, you worry about the tiny cell level at the same time, which means getting an accurate understanding of all those scales all at once requires some pretty heavy lifting with a variety of models and computational tools, which makes it quite an interesting puzzle to try to crack.
Yeah, that is fascinatingly complex. Any other perspectives that folks kind of want to weigh in on here? I encourage all of our audience members to take a look through the questions in the Q&A bar that have already been answered. And seems like there's a back and forth with some of those. So I don't know if Boris and Yarrow have seen here from Rasul a response to your question in the Q&A. Are there any questions that you'd like to be asked that you're not asked frequently enough?
Maybe the question, hey, CMMC, can you model this and this and this for me? I'm really curious what comes out.
I love that. Yeah, so seems like there definitely is a lot of brain power here that's still largely untapped by our field, and lots of folks who are working on cultivated meat research related questions, whether on the industry side or the academic side, do reach out to the CMMC to see if there are problems they can help you solve, especially as we look to grow beyond the bench scale. So it seems like, Simon, you had dropped in the chat, the best way to get involved is really to reach out at info@thecmmc.org. You can read more about the CMMC's work at the cmmc.org website. And maybe before we wrap up, because I'm not seeing any questions coming through that folks aren't already gearing up to answer, maybe this question here from Mattia. For a relatively inexperienced person, it seems that a rocking bioreactor is easy to build and gives pretty low shear stress to the cells. Is there an easy way to employ them at full scale, or would they just not provide enough gas transfer? Anyone want to weigh in on this question? Lots of furtive eye contact. Richard.
Yeah.
I was gonna say Yarrow just asked everyone to come up with something for us to model. That seems like a great example.
So yeah, I should mention actually, Radu and I were part of a GFI funded project that's still ongoing, using the same type of tools that Radu mentioned in collaboration with a company that's developing these from 2 liter to many hundreds of liter scales to answer these sorts of questions. So hopefully we'll have some answers for that soon, and then we can use the fluid mechanics that we're learning in addition to the biological side that the CMMC is developing to assess the viabilities of these things. But that's part of an ongoing GFI funded work, which we're very, very grateful for. So I hope to share those results, as well as an open source type platform for the code so that you can use as a design tool in the future as well.
Thanks, Dan. All righty. There's another question here about large-scale fermentation happening mostly in airlift reactors. And this attendee is wondering if that's something you're looking into modeling for cultivated meat production.
Not yet.
Not yet. I think one thing that's key to these airlift reactors is the bubbles that are in there, and are very there's quite some modeling in bubbles, which is a completely different type of thing to do than modeling cells or just fluids. So we don't have the expertise at the moment, I think. Maybe Radu or Daniel has. But it's definitely something that is influencing the cells. There's data on that.
Thanks, Yarrow. All righty. Before we wrap up our seminar today, are there any last thoughts that you'd like to leave our community with? Any calls to action or pieces of advice as we look ahead? And this is, again, kind of open to anyone here on the panel. It looks like some folks in the audience are interested in reaching out to have one-on-one meetings, which is kind of exactly what we're hoping for here. But any last thoughts you'd like to leave our community with before we wrap up for the day?
Well, if I may address a little bit about the question if the CMMC is only for male and computational scientists, absolutely not. It is for everyone, like Yarrow said. I'm not even a computational scientist. I'm a food scientist, but slowly getting into all the engineering aspects and doing all the CFD work. So it absolutely is for everyone. And again, whoever's willing to just join us, reach out.
Mm-hmm. Particularly if you can run experiments.
Thanks, Fernando, for addressing that. I think there was a really great discussion about gender inclusion there in the chat / in the Q&A section, and Mark Langley posted a nice suggestion for how to make our calls for participation a little bit more inclusive as well. But absolutely love the multidisciplinary approach of the CMMC. It's true that not only computational scientists are needed to solve some of these big, hairy questions. Thank you so much to everyone for participating and being willing to lend us some time, share your insight and wisdom from all of these just wicked cool projects that you have underway. I really can't wait for the cultivated meat field to get to reap the benefits of this knowledge. So much thanks to all of you, and please do keep in touch. Folks, if you are interested in learning more about the CMMC, visit thecmmc.org for more information, or email info@cmmc.org, I believe. All right, thank you so much, everyone. I will see you again next month, not for a Science of Alt Protein seminar, but rather for our State of the Industry reports, including a State of the Science webinar. So stay tuned for more details around that. Many thanks to all of the scientists and engineers who presented their findings today, and I hope you guys all have a great rest of your week. Thanks, everyone. Take care.
Thank you, Amy.